today we're releasing the OpenCrypto project, which basically aims to enable JavaCard developers and smart card developers to use the full power of the card. So my presentation, at first I will introduce briefly smart cards and JavaCards, what these are. So if you're not experts in smart cards, it doesn't matter. You will be able to follow everything. And then we'll explain what's the problem with those ecosystems and our proposed solution. And then we release certain tools that you can start using from now on. We released this morning, basically. And then we'll discuss future work if you want to get involved as well. So to begin with, smart cards. By smart cards, we mean pocket-sized card which features an embedded integrated circuit. Usually smart cards, they have a CPU and a cryptographic processor, which is aimed to do specific operations very fast. The CPU can do any operation, but it's usually slow. They usually have two types of memory. One is the persistent memory, which we have more of it, like 150 kilobytes usually. There are some cards offering up to 1 megabyte, but these are rare cases. And then there is a volatile RAM, which is very fast, but we have limited amount of it, usually less than 10 kilobytes. And of course, they have the secure random number generator, which generates us fresh randomness for keys and everything. So the smart cards are very nice because they are intended to be to operate in physically unprotected environments, so under adversarial control. And this means that they need to provide tamper protection. So by tamper protection, we mean tamper evidence. So if you manipulate the card physically, this will be visible. Tamper resistance, so it can withstand physical attacks. And tamper response, in case the card detects that it's being manipulated, it can erase keys, lock itself down, and do other things. Additionally, they also provide protection against side channel attacks, like power analysis. And then there are some periodic tests that run and check the random number generator functionality. So there are many use cases. They are being used a lot in payments, like Apple Pay, credit cards, things like this. Government cards for ID, passports, and signing. Cryptocurrencies for wallet protection. This is one of the newest use cases for JavaCards and smart cards in general. And the Internet of Things is becoming interested in them, and they try to use them as secure endpoints. So why we like smart cards? So first of all, they have a very small attack surface. So it makes it hard for the adversary to actually tamper with the hardware and extract the secrets that are stored there. They are certified to very high levels of security, even though they are very inexpensive. They are programmable, so you can build your own applications and then you run them there. And then they are suitable for very complicated business security transactions, like those used by banks and other entities. And by inexpensive, we also mean that by having like a few hundreds of them, you can essentially emulate a low-end HSM. So for smart cards, currently there are three main operating systems. One of them is Maltos. So by Maltos is geared towards being certified for high-level applications, and is usually used by bank cards and this kind of entities. So there is also .NET. I wasn't sure if I should include that here because essentially the operating system is dead. It has very limited market penetration. Very few people are using it. Honestly, I'm not aware of anyone using it, but there should be someone. And then there is JavaCard, which is the operating system we're interested in. Currently, it's run by Oracle. In the past, it was Sun. And its main benefit is that you can develop an applet for a specific card and then just take your applet and run it on another card from another manufacturer, and it's going to work out of the box. So what about JavaCard? So JavaCard started in '96. Until then, every manufacturer had its own operating system. So if you wanted to develop an application for a specific card, you had to use the operating system of that manufacturer. But then card issuers started to complain, and they demanded interoperability, which means that you can run your application on cards from different manufacturers regardless of the underlying hardware. And then indeed this happened on '97. So they founded the JavaCard forum. And they invited the Sun Microsystems at the time. And they did that because Sun Microsystems was the owner of the Java technology, and they wanted to build to run Java on smart cards. So they invited Sun Microsystems even though they had no idea about smart cards. And this was a problem in the first few meetings, but then they sorted this out. One thing that happened out of this meeting is that the manufacturers became essentially JavaCard licensees. And then the most important thing was Sun committed to periodically release the JavaCard specifications, a reference implementation, and a compliance kit. And actually, 20 years after, Oracle now keeps doing that. So they release the JavaCard specifications. These specifications are three: the virtual machine, runtime environment, and the API, which is what we're interested in. And also they release an SDK for application development, applet development. And it worked. So currently we have around 20 billion Java cards sold. The current rate of cards being sold per year is about 2 billion. And 1 billion of them were sold as contactless cards in 2016. Common use cases are telecommunications, which is when we say telecommunications, usually we refer to SIM cards, payment cards, and then loyalty cards. The API specification is what we're interested more in today. So what it does is basically it provides a list of all supported crypto algorithms and the relevant methods, and then the manufacturers take this list and implement this on their hardware. This makes it very straightforward for developers to know what's in the hardware and how they can use it. It also ensures interoperability because that list is the same for every manufacturer, so your applet is going to work everywhere. And then it allows implementations of the API to be certified both for functionality and security. And because of that, a full ecosystem has emerged and matured over the last 20 years to include laboratories and certification authorities to perform all these operations. So here is a list of, not an exhaustive list, but a very short list of the specifications released throughout the years. As you can see, with its release, new algorithms and new methods are being added. A specification is in principle released every 3 years. Sometimes it's like a bit faster, like 2 years. Sometimes it takes like an extra year, so 4 years. But in principle, it's every 3 years a new specification is being released. So what happened? All those things are very nice in theory, but in practice, this is not what's happening. So the problem is that vendors don't necessarily implement the full specification. What they do instead is they pick a subset of the functions listed there and the algorithms, and they implement that instead. This means that there is no list of algorithms supported by its card. So its card says, I comply with specification 301, and then you don't really know which subset of 301 it's in there. So what you have to do as a developer is you have to actually buy the card and check by yourself which algorithms and functions and constants are there. This actually leads to compliance problems, and here are some examples of manufacturers not really following the specification. Sometimes, even collectively, all of them don't comply. So they try to introduce RMI instead of what we're currently using in 2003. It was never adopted. There was another specification for JavaCard 3 connected, which was very nice because you could run servlets on the card. But the hardware never lived up to it, so they never implemented that, and this shows the disconnect between the people who release the specification and the actual manufacturers and what's actually possible on hardware. And then there was some discussion about an annotation framework. It was never adopted, it was just dropped. So all those things lead to interoperability problems, and you can see that since most cards run a single applet, and this was not the intention of the JavaCard ecosystem. This was not the JavaCard vision. Most applets are written and tested for a single card from a single vendor. And usually if you try to run them somewhere else, there's going to be a problem. Some algorithm is not going to be supported. And usually those problems are like you cannot recover from them. So usually vendors stick with a card. They know it works, and they don't move around. And then there is another problem that has to do with the way the ecosystem works. And it's not the manufacturer's mistake. So from the time that the specification has been released, it takes 3 years until you can start to see cards on the market supporting that, the new algorithms added by the specification. So it takes 1 year to develop the new platform for the specification, another year to test for functionality and security, and then another year to actually deploy and make the cards available on the market. So 3 years delay. And the last peculiarity of this ecosystem is that you have walled gardens. So there are all those restrictions on what you can do and all those API, let's say, deficiencies or incompatibilities. But there are also proprietary APIs. So what they do with proprietary APIs, vendors are releasing them and they provide additional classes not listed on the official API specification. And there they provide newer algorithms, mathematical operations that are not available, elliptic curve operations sometimes. And all these are vendor specific. So if you try to move from one manufacturer to the other, this API will totally make your applet not to run on the other manufacturer. Plus, they also provide these to large customers that can make a very good case. They need thousands of cards. So small development houses don't really gain access to these. And they, of course, they're very protective. You have to sign the NDAs. There is no information on the internet about them. So all these motivated us to build, to start the OpenCrypto project. The OpenCrypto project aims to reduce the time to market delay as fast as possible. So instead of having this three-year lag, we aim to speed up this to as long as it takes for someone to implement the algorithm and software. Then we also aim to improve the situation with the interoperability between cards. So our project should be able to provide a consistent library between different JavaCard platforms. And we also want to make it easy for Java developers to move to JavaCard. Because even though JavaCard and Java are similar in name, in practice they are completely different. And this change and this need is being made more prevalent because of IoT. So IoT actually needs an endpoint platform with those characteristics that JavaCard have. And, but the platform is not there yet, and it's not usable by them. So the IoT situation is the following. You have lots of small development houses, which means that they don't get access to proprietary APIs. They want to build various new things, and this means that they don't have consistent needs. So even if you add one new algorithm on the specification, it won't cover all of them. Probably it won't cover the majority of them also. And most of them are not smart card experts. So when you try to move from Java to JavaCard, and you realize that there are no strings, no integers, no garbage collection, this is a shock. So we tried to fix that. And despite all those difficulties, people have actually built lots of stuff already. Some applications are like Bitcoin wallets, two-factor authentication on one-time password generators, secure storage. And we were actually wondering, what if these people had access to the full power of the cards and they could do whatever they want with it? So the people who built that project is me, myself, Vasilis, Petrus Venda, Jordan Ezis, and Dan Svercek. And here's the OpenCrypto project. So as part of this project, we provide a math library and development tools. So the math library, as you can see on this pyramid, it sits on top of the current JavaCard API and provides integers, big numbers, and elliptic curve arithmetic. A bit more on it now. So all those classes are provided by Java. Some of them, the integers and the big numbers, are available on the JavaCard specification. But in the JavaCard reality, they don't appear in any cards. They were simply not implemented by manufacturers. And we actually implement all of them and we make them available through our library. And here is a link for the library if you want to go and download and play with it. So the integer class provides what you would expect from an integer class. So all the regular operations that an integer does in Java, we have them. The big number is geared more towards big numbers for crypto. So we do all the operations and their modular extensions so that you can build your own crypto algorithms. And the elliptic curve arithmetic is what we're most proud of because we provide all the functions that you would need when you build a crypto algorithm for elliptic curves. And I would say that we provide more algorithms, more methods from all the proprietary APIs I've seen. So here's how you use it. We try to make it as simple as possible. So when you want to define an elliptic curve, you simply create a new object and you pass the parameters for the elliptic curve, and then that's it, you have the curve, and you start generating points on the two lines below the highlighted one. And then if you want to do operations with those points, you can randomize them, you can set them from a specific byte array, or you can add the 2 points or multiply with a scalar. So in order to implement all those things, we had to handle all the low-level dirty stuff and abstract them away so that the actual user doesn't see all the ugliness going on there from the JavaCard side. So we developed a memory management that's unified. And we had to use safe reuse of pre-allocated arrays and also develop an adaptive data placement strategy, which can be either adjusted for performance or memory usage. So depending on if you want speed, you'll get to use more RAM, which you have a limited amount of. Or if you don't want to use lots of RAM, then you can use the EEPROM, and it's going to be a little bit slower. So, however, what's interesting is how you actually build such a library. Because as we've seen, the CPU is very slow. It's programmable, but it's very slow. The coprocessor is very fast for crypto, which we're interested in, but you have no direct access to it. So how would you do it? So what we did is basically we abused API calls that are known to use the coprocessor, and then we use the CPU to glue them all together. So here's a very simple example. If you want to do modular exponentiation with big numbers, what you do is basically you go to the API and you realize that, oh, RSA encryption is actually modular exponentiation, so I can use that. And then you use the coprocessor, which is very fast, but there are some limitations. These are technical problems regarding the modulo size, and here is where you use the CPU to make it all work regardless of the modulo that the user provides. And this is a very simple example. Here is a more complicated one. So the elliptic curve point scalar multiplication, which you definitely need if you want to build a crypto algorithm. It's more complicated. So as you can see, we start with a coprocessor, we do the elliptic curve Diffie-Hellman there, we get an intermediate result which we feed to the CPU, we do some processing, which thankfully it's lightweight, and then the result of that we give it back to the coprocessor, and then we get the final result. So there is a bit of back and forth between the coprocessor and the CPU. And of course, you may be wondering how fast this is. So here is our timings for elliptic curve operations. We are all, depends on, as you can see, it depends on the card. Some of them are faster, some of them are slower. Usually it's, the slowest operation is multiplication, which runs up to 4 seconds. I haven't seen anything slower than that. And then we also have these operations, which are for big numbers. These are all less than a second, and they happen very fast because they are simpler. And of course, some cards do better than others. This was one of the tools we are releasing, the library. We also released the profiler. So the profiler is basically aims to fill in a gap that exists right now in the ecosystem. If you want to do speed optimizations, it's notoriously difficult in JavaCard. And there is no free profiler available, simple as that. So we released the profiler. Here's the URL. You can go on there and download it. If you want to use it, here are the steps. First, you need to insert some performance trap on your source code. Just a single line that it tells the profiler, this is the function I want to, or the API call I want to profile. And then you run the automatic processor, and the result you feed it into the profiler, which executes your applet multiple times, and then annotates the code with the measured timings for each one of the lines you're interested in. So on top of that, we also have this other project, and this is the third thing we released today. So what we did, as we said, is that if you buy a card, you don't really know what's in there. You have to test by yourself. So we bought a bunch of cards, more than 60 actually, and we tested them for 230 algorithms, and we released a huge table which basically says which algorithms are supported by which cards, and also discusses the performance of each card. Because as we've seen, the performance differs. And here's the development cycle. So how would you develop a JavaCard applet if you're interested into jumping into the ecosystem? So first, you find a suitable card. This was not possible until now. You can go to our table and find the coverage that satisfies your application. And then you can use your favorite ID. Anything that supports Java should work. Then you use the JavaCard sim as a simulator. I wouldn't advise anyone to debug on the card. It's very time-consuming, counterproductive. So first debug on the JCard simulator, and then you can build your applet using Maven and JavaCard scripts. And Global Platform Pro will allow you to upload this to the card, and then you do your profiling if you want to enhance your performance. So apart from these, we're working on some other stuff. First one is basically semi-automated porting to JavaCard. So what we want to do is to make JavaCard even more accessible to Java developers. And this is further amplified, this need, by the need for endpoint security. So it would be very nice when we have Java crypto code, if Java developers were able to easily move it to JavaCard as a secure element and run it there. So we have we are building this porting app that will allow you to do that on a semi-automated manner. And then we have the JavaCard crypto lib, which is essentially a collection of crypto algorithm implementations. And what we aim to do is we aim to minimize that 3-year gap that exists between the specification and the actual world. So people can develop their own algorithms as it happens with larger libraries like Bouncy Castle and other libraries, and then put it there for everyone to use or audit. And if you're interested, we would be very happy if you would like to contribute with the algorithms that you're interested in. So if you have a use case and you build an algorithm for your specific use case, you can put it in the library and it's going to be there for everyone to use and audit. And here are the takeaways for our presentation. So first, we released the JavaCard math lib. Developers are now free to build their own applications. They don't have to rely on the specification anymore or the manufacturers to implement the algorithms. And also, we have, unlike everything else in JavaCard, we have examples and documentation. So we try to make it super easy for people to use. Then we also have the performance profiler, which also would hopefully help people to profile and increase the performance of their applets. And then finally, we have the coverage and performance survey table, which features more than 60 cards and tests for about 230 algorithms. You can find all these on that URL, so we'd be very happy. And yeah, that was it. Thank you. Okay, we have a question.
Yeah, so in many cases, the JavaCards are necessary to require FIPS 140-2 certification for applications.
Could you use the microphone because I cannot hear you very well? I'm sorry.
Hi. So in a lot of cases, that's loud. In a lot of cases in banking and authentication use cases, you need FIPS 140-2 validation on some of these cards. Are you planning to either submit, because that's what Bouncy Castle does, right? They submit for 140-2 and they get a level 1 certification on their library. Mm-hmm. Would you do that with this library, or how does that interplay with the security validations on the cards?
Okay, that's a very good question. I think first we'll start building a collection of algorithms, and then we'll start to think up more seriously about moving that way. So I think it's a bit further down the line. So first we need to have the actual algorithms. Right now we're not there yet. We have all the math operations, and that we can possibly move on that way. But right now we're not certified. That would be very interesting actually to do, yes. And if there are other libraries doing that, which of course there are, we can basically follow them in the actual process of it. Another question?
Yeah. Please. Can you go back 2 slides to the workflow, please?
The workflow.
And the question is if number 3 here, debugging using JCard Simulator, would be practical as a first step for those new users that don't know how to find a suitable card. Would it be good for that, without buying one and realizing it's the wrong one?
Mm-hmm. So that's a very good question. So what I would suggest is you don't buy a card before you reach step 3, and you can definitely do that. So you build your application, and then you check, okay, which algorithms I've used. If you know from the beginning what you're going to use, fine, you can use our table on step 1. But in some cases where you start building and you're not sure how you're going to do it, then you can use our table and find which cards fully supports what you want to do. And then you go out and you find a card that fits your purposes. Or on top of that, if it's very likely that our library covers your needs, so you find a card that works very nice with our library and it's fast on what you want to do, and you do that instead. So you have 2 alternatives. Either you find a card that out of the box supports everything you want to do, or you find a card that doesn't support everything, but it runs very well with a library which supports your applications. Thank you.
Quick one over here. Have you worked with any of the vendors or with Oracle on any of this? Like any of this JavaCard vendors, Tumulto or any of the others?
So not really. We're not cooperating with any of them. I know that some of them, they have proprietary APIs. And it would be very nice if they decided to open those APIs, maybe motivated by our library. But that's left to see. And I think this ecosystem is notoriously slow into changes. So let's see in the next few years how it's going to go. OK, thank you. I'll do a wrap-up session, so if you have more questions.